You don't necessarily need to write it down, no, but these are up on DMAP. Hello to everyone listening at home. So, we look back at the stuff we're talking about in an atom, all right? When I talk about a neutral atom, I'm talking about the number of protons in the nucleus and the number of electrons orbiting the nucleus being the same, okay? So, if you lose an electron, however, you will no longer be neutral. You will have a slight charge. If you gain an electron, however, you will no longer be neutral because the proton charges balance out the electron charges. And as soon as you do that, you get an ion. And there are a different number of electrons in an ion to the number of protons. So, Christoph, if I had more electrons than protons, what would my charge be as an ion? Negative, correct, because there's more negativity there. Conversely, Matt, if I had more protons than electrons, what would my charge be? Positive, yeah, because I told you conversely, and that's the opposite of what Christoph said. So, it's all to do with negativity. How much negativity does one thing have, or how much positivity does another thing have? So, for example, ions are charged atoms. There are a different number of electrons to protons. They are formed when an element either loses or gains electrons in a chemical reaction. So, sodium here has 11 protons. It has a charge of +1, so that must mean it's a sodium ion. So this sodium ion has 11 protons, because that's its atomic number, but it's only going to have 10 electrons. It's lost one. And as soon as you lose a piece of negativity, you're going to get a positive charge. Think of it as bad thoughts, all right? If you lose a bad thought, you start feeling happier. Start feeling more positive. If you gain a bad thought, it's going to bring you down, all right? So it's like the sodium has lost that negative thought, that negative electron, and now it's one up. Now it's positive. Conversely, a sulfur atom is going to take 2 electrons, all right, to form a sulfur 2- ion. So it's gained 2 bad thoughts. Now it's doubly negative, all right? 16 protons, but 18 electrons, okay? It has 2 electrons more, therefore 2 negative charges more. So let's talk more about these electrons, all right, and electron configuration. The electrons of an atom are not arranged randomly. They exist in shells, all right, spaced out from the nucleus. They are negatively charged, but they do tend to pair up, all right, much like girls going to the toilet. That was sexist a few years ago, and I forgot to take it out. But the point is, right, they pair up. They like to be with another electron spinning next to it. All right? They don't like being lonely. They can pair up because they spin on their axis and generate a magnetic field. So one will spin one way and the other will spin the other way whilst they're going around the orbital. And that allows them to pair up because there's a magnetic direction going one way and a magnetic direction going the other way. And so they get in sync, all right? And 2 electrons spinning on their axis in the opposite direction will be attracted towards each other because opposites attract again, all right? So if you've got a magnetic field going one way and one going the other, they'll start to attract. That's a bit more complicated, and I don't expect to go into spin just yet, but just be aware that they pair up. How many of you, when you're asked by your teachers to do something, always take a friend with you? Yeah. You get real lonely. You can't handle being alone with such responsibility as getting a photocopy. Taking the role to student services. Do you hold hands when you do that, Coop? Or? Yeah, good. It's good. Okay. I'm going to move on. Now, the maximum number of electrons that each shell can hold increases as your distance from the nucleus increases. Why is that? Well, who's ever blown up a balloon? Right? When you blow up the small bit, you've got less of a balloon. Then you keep blowing, it gets wider. There's more space, then wider again as you keep blowing up. Okay? As your radius improves, you've got more three-dimensional space. And then once you do that, you've got more room to fit electrons. So the further away from the nucleus, the more electrons those shells can hold. Because there's more volume. All right? But the force of attraction will start to decrease. All right? The further they are away. Remember, in the nucleus, you've got that positive proton-based nucleus with the positive charge. But the further away you go from that charge, the less likely it's going to hold on to it. That's why atoms that are lower on the periodic table are far more reactive. Francium, you could turn into a bomb if you've got a bathtub full of water. All right? You've seen what sodium does in a bucket of water. Imagine francium in a bathtub. It's so reactive, it's because it can't hold on to its electron very well. So automatically the electron goes, I'm out, and goes and reacts so rapidly that it generates heat and hydrogen gas, and then you get the explosion. Okay? So the reactivity is going to change, and we'll look more closely at that when we start looking at electronegativity. But just be aware that the force will decrease, and there's a special law. Does anyone know the law that dictates that concept, the idea of charge reducing as the distance increases? It's a physical term. You might have come across it in physics last year. The law is Coulomb's law. Okay? Yeah. And we have a short formula used to work out the maximum number of electrons each shell can hold, which is 2n squared, where n is the number of the shell. So in the first shell, so you got your hydrogen first shell, it's 2 times 1 is 2. All right? Well, 1 squared is 1, and then it's 2 times 1. So hydrogen can hold 2 if it really wanted to. Okay? It only has 1. But in the first shell, you can have a maximum of 2. In the second shell, you can have a maximum of 8, because 2 squared is 4, 2 times 4 is 8. And just so we can have that closure, in the third shell, you can have 18. 3 squared is 9, 2 times 9 is 18. Yes, Joel?
Don't they tend to do 8 and then, like, once it does 8, it kind of fills up other ones sometimes?
Yeah. You can get, you do your 8 and then you'll do another 8 and then you might get like a little extra on the side forming into the fourth shell.
Yeah.
You are right. Yeah. And that's what I was talking with Isaiah about, is that those energy levels start to cross over. And so that's transition metals, they'll do that quite a bit.
That's why we're not looking at that. Are we?
Not just yet.
Yeah.
We want to be looking at the first 20 for now, and then I'm going to expand on that, okay?
Yeah, so this year when we go into like third and fourth shell, because last year we kind of stuck in the first 3 months.
Yeah, we're going to look more at the fourth shell stuff towards the end, and I want to look at that when we come to electronegativity, all right? Because that relates to how well it's holding on to the electrons. But just know that as a general rule, in the third shell and in the fourth shell, you can have 32 as a maximum, and in the fifth shell, you can have 50 electrons altogether, all right? But they'll have different suborbitals within that. Now, we'll go into suborbitals later. What I want you guys to know is that there are these shells, and each shell has a different distance away from the nucleus. Kind of like the moon is away from the Earth. You have an orbit, and then you've got, your satellites around the Earth. They have different distances and can fit more things in. So, we actually assign the shells a name, believe it or not, or a letter, I should say. Okay? And we don't do A, B, C, and D, because that would be being too straightforward and easy and logical. Why? It's because there are so many questions in chem that start with A, B, C, or D. And if you just go with K, L, N, L, P, it just separates them conceptually. I think. I don't know. I honestly don't know. I never questioned it. I think it has to do with the fact that we spend so much time with A's and B's all the time that it's just easy to go K, L, N, N, O, P. And electron capacity in the K shell, the first shell is 2, L shell is 8, and again. All right. Now, these two never get filled completely. All right. That's when you're getting into those actinides, lanthanides, the real big atoms. I want to be looking around up to here, 3rd and 4th by the end. Okay? By the end of year 11, semester 1. So, logically, it follows a mathematical progression. 1 pair, 1 pair plus 3 pairs, 1 pair plus 3 pairs plus 5 pairs, 1 pair plus 3 pairs plus 5 pairs plus 7 pairs. So 2, 8, 18, 32. All right? They start pairing up as they go. That's just to separate, just to show you where I'm getting those numbers from. I'm going to hand out a sheet later on which will have all the electron configurations for the main shells for the first 36 elements, okay? The first 36. It's expected that you learn the configurations for the first 36, and I will help you with that. It's just a stupid cartoon. All right, I might pause it there. So that was electron configuration.